Usually when we talk about a metal getting hot, there's this default expectation of just simple, disorganized chaos.
Oh, absolutely. Yeah.
Like imagine putting a heavy copper pan on a roaring stove.
Yeah.
And in our minds, the atoms immediately start vibrating wildly, right? The electrons just sort of decouple and start bouncing around like tiny hyperactive pinballs.
Right, like a microscopic mosh pit.
Exactly. And a physicist standing nearby just points at the mess and says, well, there it is. That's kinetic energy doing its thing. We have this deeply ingrained assumption that adding heat simply means adding disorder.
I mean, it is entirely intuitive to think that way. We're macroscopic creatures, and in our macroscopic world, heat melts ice into water. It turns water into steam.
That breaks things down.
Exactly. It breaks rigid structures down into fluid, chaotic ones. So we are heavily conditioned to associate thermal energy with a loss of underlying architecture.
Hot or cold, it feels like a very clean binary transition from order to that mosh pit we just talked about.
Mm-hmm.
But then you step into the world of low-temperature electron thermodynamics.
Which is a very different world.
It really is. And you bring your macroscopic intuition with you, and suddenly, well, you realize that mosh pit is frozen. Or at least it's not behaving like a mosh pit at all.
Right.
We're looking at a microscopic landscape that is stubbornly, weirdly rigid.
Right.
And it forces us to ask what should be a rudimentary question, which is, what is actually happening inside a metal when it gets hot?
Because the closer you look at it, the less it looks like random bouncing.
Yeah.
And the more it looks like a highly regulated, almost bureaucratic exchange of energy.
Bureaucratic. I love that word for this.
It's remarkably apt there, I think. At the quantum level, energy redistribution doesn't just happen because it wants to. It happens because it is allowed to by the underlying architecture.
Right.
What we perceive as heat at the level of individual electrons is heavily governed by strict statistical rules. It completely defies that common sense, macroscopic intuition of heat as a pure chaotic frenzy.
And that profound disconnect between the mosh pit we imagine and the regulated architecture that actually exists is exactly what brings us to today's deep dive. We are exploring a highly detailed and, frankly, a paradigm-shifting 2026 physics paper by Philip Lillian.
Yes.
It's titled Electron Heating as Fermi Broadening plus Projected Coherence Redistribution, which is a mouthful.
It is a bit of a mouthful, yes.
But I want to set the table for you right now for everyone listening. The mission here is not to get bogged down in a blackboard full of esoteric equations. The goal is to extract the core aha moment of Lillian's work.
And there definitely is one.
Right. We are going to explore how a radical new concept called projected coherence might completely redefine our understanding of low-energy electron thermodynamics. And honestly, the absolute best part of this paper, it manages to introduce this massive, sweeping concept without completely throwing out the classic textbooks.
The restraint shown in this paper is incredibly rare for theoretical physics.
Oh, for sure.
Usually, when a theorist proposes a concept as grand as a universal field tensor, which we will absolutely get into later, the instinct is to claim that the old models were completely wrong.
Just tear it all down.
Exactly. But Lillian doesn't do that. What's so compelling about this work is how carefully he threads the needle. The true beauty of this paper lies in its strict falsifiability.
Yeah, that part blew my mind.
He doesn't just present an elegant mathematical idea and leave it to philosophers. He provides an exact, rigorous, and frankly punishing roadmap for how experimentalists can prove his theory completely wrong.
I love that so much. It is incredibly exciting when a new scientific paper doesn't just show up with a wrecking ball to bulldoze the old theories. Instead, Lillian elegantly builds this massive, hidden structural basement underneath the existing house.
That's a great way to put it.
He's basically saying, look, the house is fine, but you don't realize what it's sitting on. But before we can understand that new structural basement, we really have to make sure we're crystal clear on the architecture of the house itself, right? We need to look at the standard textbook model of electron heating.
Establishing that baseline is critical. If we don't fully appreciate why the standard model works so well, Lillian's refinement will just seem like arbitrary math.
Right.
The house you mentioned is built on Fermi-Dirac statistics, and specifically the Pauli exclusion principle.
Okay, so since we were talking about electrons, we know we're dealing with fermions.
Yes.
And they have that fundamental property where no two fermions can occupy the exact same quantum state simultaneously. Like they refuse to share.
They are very antisocial particles in that regard.
Right, exactly. So when we picture a metal at absolute zero, we know the electrons stack up, filling the available energy states from the bottom up all the way to what we call the Fermi surface.
Precisely. And because of that strip stacking, when we introduce thermal energy, when we heat the metal up, the vast majority of those electrons are completely trapped.
They're boxed in.
Exactly. An electron deep down in the energy band might absorb a photon or a phonon and want to jump to a higher energy state, but the states immediately above it are already occupied. Pauli exclusion completely forbids the jump.
So it's locked in place. You know, I always like to think of this using a water cup analogy.
Okay, let's hear it.
So the density of states is the shape of the cup, right? And the electrons are the water. Heating the metal isn't like boiling the whole cup of water from the bottom up. It's more like a gentle breeze sloshing the water right at the very surface.
That's a very accurate visualization.
The deep water, the electrons deep below the Fermi energy, doesn't move at all. The only electrons that can actually utilize that thermal energy to jump into empty states are the ones right at the meniscus, right at the Fermi surface.
And that is the absolute essence of standard thermal occupation broadening.
Mm-hmm.
Only a tiny fraction of the electrons residing within a very narrow energy shell around the Fermi level, roughly equivalent to the thermal energy, which we call KBT, are thermally active at low temperatures.
Right.
And it's vital to acknowledge just how phenomenally successful this simple model is.
Mm.
It is the absolute bedrock of condensed matter physics. It perfectly predicts the Sommerfeld linear heat capacity law.
Oh, right. That's the observation that at low temperatures, the electronic heat capacity scales linearly with temperature, right? The C equals gamma T relationship.
Exactly. The fact that only that tiny surface layer of electrons can absorb heat is exactly why the heat capacity is linear, rather than constant like classical physics would predict.
Makes sense.
The standard model also perfectly predicts the thermally broadened Fermi-edge structure we see in ACARPs.
Which stands for angle-resolved photoemission spectroscopy, for those keeping track.
Yes, thank you. If you look at the Fermi function at 0 temperature, it's a perfect, sharp step function. Occupied states are at 100%, and then they instantly drop to 0% right at the Fermi energy.
Like a cliff.
Like a cliff. But as you heat it, that sharp cliff edge blurs. It rounds off into a smooth curve. Standard Fermi-Dirac statistics models that smearing with breathtaking accuracy. And furthermore, it also models the conventional nonequilibrium relaxation times we measure in the lab.
Okay, let's hold right there. Because if this water cup model is so bulletproof, if it accurately predicts the Sommerfeld coefficient, and it perfectly maps the edge blurring we see in spectroscopy, and it handles the relaxation dynamics, why fix it?
That's the million-dollar question.
I mean, physicists are pragmatic people. Why is Lillian writing a highly dense, mathematically exhausting 60-page paper to mess with a textbook model that clearly isn't broken?
And that skepticism is exactly where the breakthrough happens. The water cup model works perfectly for the energetic cost of the splash. It accurately describes how much thermal energy is required to move an electron from an occupied state below the surface to an empty state above the surface. But it makes a massive silent assumption.
Which is?
It assumes that every single available empty state, every drop of space at the surface, to use your analogy, is completely identical in its underlying structural stability.
Oh. It assumes the only thing the electron cares about is the price tag, the energy cost.
Exactly. It treats the quantum states as nothing more than energetic parking spots. If an electron has the requisite thermal energy to jump into an empty spot, it just jumps.
Right.
The standard model assumes there is no hidden architecture, no underlying structural grid that might make one empty state fundamentally more preferable to another empty state of the exact same energy. Lillian argues that this purely energetic view is incomplete, and that missing structural dimension leads us directly to his proposed extension.
And this brings us to the absolute star of the show, the coherence shift. Lillian introduces this concept of the universal field tensor, or UFT. He's essentially saying that the old equation we all learned, that electron heating equals Fermi-Dirac occupation broadening, is missing half of the picture.
He is adding a fundamental second term. His new synthesis posits that electron heating equals Fermi-Dirac occupation broadening plus projected coherence redistribution.
Projected coherence redistribution. We really need to unpack that because it sounds like buzzword soup until you drill down into what he's actually claiming.
It does sound intimidating. Let's start with the coherence part. Lillian introduces the projected coherence factor, which he denotes mathematically with the Greek letter chi.
Right.
Functionally, this factor acts as a stabilizing weight on the occupied electronic density of states.
A stabilizing weight. So in the standard model, the density of states is basically just an inventory system, right? It just counts how many available states exist at any given energy level.
Right, it's just a head count.
But Lillian is saying, sure, count the states, but then you have to multiply that count by this new underlying coherence factor, this chi.
That is the perfect way to frame it. The standard model asks, is the spot empty? Lillian asks, is the spot empty, and how structurally sound is it?
Oh, wow.
This chi value represents the degree to which those occupied states remain structurally stabilized, or what he calls coherence concentrated.
But where is this structural stability actually coming from? Because if it's not coming from the atomic lattice and it's not coming from the electron interactions in the traditional many-body sense, what is providing the coherence?
This is where Lillian zooms the camera way, way out. He introduces the universal field tensor, denoted mathematically as a specialized blackboard bold U. He posits this UFT as the primary coherence-bearing field object in the universe.
The universe. Wait, he's making a cosmological level claim to solve a low-temperature thermodynamics problem.
He is. He suggests that the electronic sector we are measuring in a tiny piece of copper in the lab is just a projected regime of this broader universal coherence field.
That's wild.
The UFT projects down into our localized electronic system through a specific mathematical operator. So the electrons in the metal are essentially constrained by the structural shadow of this universal tensor.
The structural shadow. I really, really like that framing. The metal we're holding in the lab is catching the shadow of a massive universal structural grid, and the electrons have to navigate their thermal jumps within the confines of that shadow.
And Lillian formalizes this navigation mathematically using closure stability eigenvalues, which he calls kappa n.
Okay.
Now, I know we said we wouldn't get bogged down in the math, but the concept here is quite elegant. Each specific quantum state gets a kappa n value. Larger values mean the state is strongly closure stabilized by the UFT.
Yes. Right.
The structural shadow is holding that state firmly in place. It's robust. Smaller values mean the state is weakly stabilized. It's loosely held, frail, and therefore much more susceptible to being disrupted by thermal fluctuations.
Let me push back on this a bit, or at least try to ground it in a sensical analogy, because visualizing a universal tensor's structural shadow gets a bit, well, ethereal.
It does, yes.
Let's go to an apartment hunting analogy. We have our electrons, and they're gaining thermal energy, which is like getting a raise at work. They suddenly have the cash to move out of their low-energy apartment and move into a higher-energy vacant apartment.
Okay, I follow.
Standard physics says the electron only looks at the rent price. If it has the cash, it moves. But Lillian is saying the electron also hires a structural engineer to inspect the new apartment building.
I see exactly where you're going with this.
Right. The closure stability, that kappa n value, is the structural integrity of the building.
Yeah.
So electron are looking at two empty apartments. One is slightly more expensive in terms of energy, but it's built out of reinforced steel that has a massive kappa n value.
Right.
The other apartment is slightly cheaper energetically, but it's built out of wet cardboard. It has a terrible kappa n value. Lillian is arguing that the electron's thermal movement is actually biased toward the reinforced steel apartment, even if it costs a bit more thermal energy to get there.
That is an excellent translation of the concept. The movement of the electrons is biased. The entire pipeline of how states are occupied, which Lillian calls the closure-weighted density pipeline, is completely transformed.
Because they're picky now.
Exactly. Electrons are no longer just blindly moving up a simple energy ladder based entirely on the energetic cost. Their movement, their redistribution, is weighted by how structurally stable the new states are within the UFT's projection.
This means that when we heat up a piece of metal, we're actually inducing two entirely distinct phenomena simultaneously.
Yes. Thermal variation now comprises two parts. First, you have the familiar thermal broadening, the electrons gaining kinetic energy and attempting to jump up.
The normal stuff.
The normal stuff. Second, you have the closure coherence redistribution. The electrons deliberately shifting their occupation to align with the underlying structural stability grid provided by the UFT. Heating is no longer merely a scalar redistribution in energy space. It becomes a joint redistribution across both energy space and coherence space.
I have to admit, conceptually, that is gorgeous.
It really is.
The idea that there is an energetic reality and a structural reality working in tandem to dictate quantum behavior feels deeply satisfying. It makes the universe feel less chaotic and more deliberate.
It restores a sense of order.
Yeah. But, and this is a massive but, in theoretical physics, elegance is cheap.
Very cheap.
You can build the most beautiful mathematical apartment building in the universe, but if I can't measure the difference between the steel and the cardboard in the laboratory, it's just philosophy, you know? It's not physics. how do we actually see this invisible structure altering properties we can measure?
That is the exact hurdle Lillian has to clear, and it transitions us perfectly into how he addresses the observational data. He knows the theory must leave a measurable footprint, so he targets the most fundamental low-energy observable we have, the thermodynamic channel, specifically the heat capacity.
Okay, so we're back to the Sommerfeld coefficient. We're looking at how this new structural bias alters the way the metal absorbs heat.
Correct. Lillian introduces a minimal perturbative profile to see exactly how his projected coherence factor, the chi, alters the standard thermodynamics equations. He uses a simple linear equation to model the local closure profile near the Fermi surface, which is phi of E equals A plus B times E minus EF.
Let's translate those parameters because
Right.
they are the absolute linchpin of the entire paper. We have A and B,
And we also have epsilon, which is simply a very small dimensionless coupling parameter.
just to keep things mathematically sound.
Exactly. Its presence just ensures that we are treating this structural shift as a small perturbation to the standard model, not a complete rewriting of the energetic laws. But the physical meaning is carried by A and B. The parameter A represents the local weighting. It tells us the amount of coherence retention exactly at the Fermi surface.
So we go back to the water cup. A is just asking, right exactly at the meniscus or at the surface level, how structurally stable is the water?
Yes. And the parameter B is the closure slope. This is arguably the more critical parameter. It represents how rapidly that coherent structure changes as you look at states just slightly above or just slightly below the Fermi surface.
So B is asking, does the structural stability increase as we go up in energy, or does it decrease? Again, is the UFT shadow getting stronger or weaker as we move away from the Fermi level?
Precisely. So Lillian takes this new coherence-weighted profile, armed with parameters A and B, and runs it back through the standard thermodynamic integrals. He recalculates the heat capacity. And the mathematical outcome is striking. The Sommerfeld coefficient, that gamma that dictates linear heat capacity, is renormalized.
It fundamentally shifts.
It shifts. The new heat capacity coefficient, which we'll call gamma C, equals the old standard gamma 0, but multiplied by a new factor, 1 plus epsilon times A plus EF times B.
So gamma C equals gamma 0 times 1 plus epsilon A plus EFB. The capacity we measure in the lab is directly modified by our stability score A and our stability slope B.
That's what the myth says.
And on paper, that seems like a massive victory, right? We just go into the lab, we measure the heat capacity of a sample at low temperature, we see that the measured gamma is different from the textbook prediction, and boom! We've proved the existence of the universal field tensor. We found the invisible structure.
Well, that assumes we are stopping our critical analysis there. And the reality of experimental condensed matter physics is far, far more complicated. And to Lillian's immense credit, he is brutally honest about the next part. He calls it the identifiability problem.
Wait, why is it a problem? If the math predicts a shift and we measure a shift, isn't that science working perfectly?
The complication there is that if we only look at heat capacity, this predicted shift in gamma is observationally degenerate with standard Fermi liquid theory.
Degenerate, meaning mathematically indistinguishable from something we already know about.
Exactly. Let's delve into the history of this for a moment because it's vital. For 70 years, the bedrock of this field has been Lev Landau's Fermi liquid theory. Landau recognized early on that electrons in a metal don't just ignore each other, they interact constantly.
Right.
But instead of trying to calculate the infinite complexity of all those interacting electrons, Landau said, let's just treat them as if they were free, non-interacting electrons, but we will pretend they are slightly heavier. He invented the concept of the quasi-particle.
Ah, right. The effective mass. The ultimate rug sweeper of physics.
It really is. In standard condensed matter physics, if an experimentalist measures a heat capacity that is anomalously high, the theorists don't panic. They just say, the electron-phonon interactions or the complex band structure are making the electrons act sluggish. They have a higher effective mass. They denote this effective mass as m star.
Okay.
And here is the devastating part for Lillian's thermodynamic equation. Any theory that tweaks the low energy density of states produces this exact same shift in the linear heat capacity.
Oh, so if I'm picturing a scale in my mind, on the left side, I have Lillian's elegant closure shift driven by his structural parameters A and B.
Right.
And on the right side, I just have standard Landau physics slapping a multiplier on the mass of the electron, the m star. The scale perfectly balances. They output the exact same anomalous heat capacity number.
They are completely identical if you only measure the heat capacity channel. A single channel measurement provides absolutely no way to distinguish between an electron acting heavy because of local interactions and an electron acting heavy because it's navigating the structural shadow of a universal field tensor.
I have to admit, that feels a bit deflating. If I measure an anomaly in the lab, Lillian's model says, aha, look at the projected coherence. But standard Fermi liquid theory just yawns and says, nope, just a heavier effective mass, move along.
It does.
If aim-star does the exact same job, why do we need this incredibly complex UFT framework?
Yeah.
Isn't Lillian just putting a very shiny, very mathematically intimidating new label on an old, well-understood box?
If the paper ended at section 3, yes, it would be nothing more than a relabeling exercise. And any rigorous peer reviewer would reject the paper on those grounds immediately.
I'd hope so.
But Lillian anticipates this exact criticism. He acknowledges that a single thermodynamic channel proves nothing. To break the tie between standard effective mass and true projected coherence, the theory must constrain other physical observables simultaneously without changing the parameters.
Okay.
And that bridge leads us directly to the core brilliance of the paper, the minimal empirical triad.
The triad, this is where Lillian forces his theory to put its money where its mouth is.
Yes. Non-trivial physical content, meaning proof that the UFT actually exists and isn't just an effective mass illusion, only appears when one shared underlying low-energy structure constrains thermodynamic deviations, spectral deviations, and dynamical deviations together.
Okay, we've already covered the first leg of the triad, the thermodynamic channel, the heat capacity. We know we need A and B to shift the Sommerfeld coefficient. Now let's look at the second leg, the spectral channel. This is where we look at the Fermi-edge itself.
Right. We discussed earlier how heating blurs the sharp step function at the Fermi surface. That's the thermal edge. We can measure the precise shape of this edge using techniques like AirRP.
Right, the spectroscopy.
Now, if we apply Lillian's coherence weighting to the mathematics of the Fermi edge, the effective width of that thermal blur, which we'll call WC, fundamentally changes.
And the formula for the new width is fascinating. It's WC equals W0 times 1 minus epsilon A plus 2 epsilon BK BT.
Let's dissect that. The original expected width, W0, is modified by our old friends. The coupling parameter, epsilon, the local weighting, A, and the closure slope, B.
So the parameter A rescales the thermal width linearly. But the truly interesting part is that last term. The closure slope, B, is multiplied by the Boltzmann constant and the temperature, the KBT.
And that specific coupling to temperature is what sets the UFT apart. What happens when the closure slope, B, is non-zero?
I don't know what happens.
If B is non-zero, the Fermi edge doesn't just get uniformly wider or uniformly narrower as you heat it. Because of how the linear slope interacts with the exponential thermal distribution, the Fermi edge develops a characteristic asymmetric skew.
A skew. So the curve isn't a perfect symmetrical blur anymore. It bulges or leans heavily to one side of the Fermi energy.
Exactly. And this is a massive differentiator. An ordinary effective mass enhancement, the M-star from Landau theory, just makes the quasi-particles look uniformly heavier. It scales the density of states uniformly.
Just symmetrically.
Right. It does not inherently predict a specific temperature-dependent asymmetric skewing at the Fermi edge, but Lillian's coherence model demands it, assuming B is not exactly zero.
Okay, so we have the heat capacity shifting, which gives us the values for A and B. We take those same values, plug them into the spectral equation, and look for an asymmetric skew in the ARPS data. That's 2 legs. What is the final leg of the triad?
The dynamical channel. This is the realm of nonequilibrium relaxation, the recovery phase.
Right, so we are shifting from static measurements to dynamics.
Right.
What happens when we kick the system out of equilibrium?
Imagine you hit the metal sample with an ultra-fast laser pulse, a femtosecond pump pulse. You instantly inject a massive amount of thermal energy into the electron population, shoving them violently into excited states high above the Fermi level.
Okay.
And then, using a probe pulse, you watch how fast they relax back down to their normal, low-energy baseline.
You kick the mosh pit into overdrive, and you time how long it takes for the music to stop and everyone to find their seats again.
Exactly. Standard physics dictates that these excited electrons just need to dissipate their excess energy. They do this mostly by bumping into the atomic lattice, releasing phonons, and slowly bleeding off the heat.
Sweating it out.
Right? There is a standard expected relaxation time for this energy dissipation, which we call tau zero.
But in Lillian's UFT framework, the electrons aren't just trying to dump energy. They have a second job.
They do. In the UFT framework, the excited electrons must undergo a reclosure process. They don't just need to dissipate energy. They have to find their way back to their stable coherence structure within the UFT grid. They're seeking structural stability.
Going back to the apartment analogy, they can't just move into any low-energy apartment. They are frantically searching the city for the apartments built with reinforced steel. They have to find the high kappa N states.
Precisely. And because they are searching for specific structural stability rather than simply bleeding off energy to any available state, Lillian predicts a heavily modified relaxation time, which he calls tau c.
The closure-modified relaxation time. And I'm assuming the parameters A and B show up in this equation too.
They dominate the equation. The modified relaxation time tau c equals the standard tau 0, multiplied by a very complex bracket.
Of course it is.
It's 1 minus epsilon times a fraction involving lambdas and gammas plus a and b. Now, we don't need to define every lambda and gamma there. They relate to standard scattering cross-sections.
Let's spare everyone the calculus.
Agreed. But the critical takeaway is that the dynamical relaxation is intrinsically hardwired to A and B.
And here's where I think the paper drops its biggest bombshell. Depending on the exact sign and magnitude of that closure contribution, the system doesn't just relax slightly differently. It can create a severe, measurable relaxation bottleneck.
Yes. If the closure contribution is negative, if the UFT structural grid is particularly unforgiving, the system takes significantly longer to relax than standard electron-phonon dissipation models could ever predict.
Wow.
The excited electrons get bottlenecked trying to find their proper coherence structure. Tau c becomes dramatically greater than tau 0.
They get stuck in traffic trying to get to the reinforced steel apartment.
It's a perfect analogy.
So if we pull all of this together, Lillian is saying that the exact same values for A and B that cause the ambiguous shift in heat capacity must be the exact same values causing the asymmetric skew in the spectrometer, and they must be the exact same values causing the electron traffic jam under the ultrafast laser.
That is the crux of the theory. It relies entirely on cross-observable parameter reuse.
Let me try another analogy here, because this is the make-or-break moment for the theory. Let's say A and B are the numbers to a combination lock.
Okay.
Lillian is saying you can't just use your combination to open the thermodynamic safe, find an anomalous heat capacity, and declare victory over standard physics. Because standard physics has a skeleton key called effective mass that opens that safe too.
Right, the degenerate channel we talked about.
So to prove the UFT exists, you have to take that exact same combination, the precise numerical values for A and B that you derive from the heat capacity, and walk over to the spectral safe. You type them in. Does it perfectly predict the skewed Fermi-edge? If yes, the safe opens.
And then you move to the third safe.
Right. You walk over to the dynamical safe. You type in the same combination again. Does it perfectly predict the ultra-fast relaxation bottleneck? If yes, the third safe opens. If the combination fails on even one safe, the whole coherence theory is busted.
That is a brilliant way to conceptualize it. The model intentionally, deliberately risks its own destruction by demanding this rigorous cross-observable consistency.
It's so bold.
It really is. An effective mass parameter, m star, only opens the first safe. You cannot logically take an effective mass multiplier and easily plug it into a formula to simultaneously predict a specific temperature-dependent asymmetric edge skew and a specific reclosure relaxation bottleneck. It just doesn't work.
It falls apart.
Lillian's structure forces all three phenomena to be intimately linked by a common underlying coherence geometry.
That is just a massive flex for a theoretical physicist. To put your entire mathematically beautiful theory on the line like that. I mean, most theorists want to build a model with so many adjustable parameters that it can fit any data you throw at it. Lillian has deliberately removed the safety net. And that realization brings us to section 5 of the paper, the explicit falsifiability matrix.
Yes. Lillian goes beyond just suggesting an experiment. He dictates a strict, 3-level experimental protocol for testing his theory in a lab. He is essentially giving experimentalists a manual on exactly how to destroy his life's work.
I want to walk through this protocol step by step because it's a master class in the scientific method.
Let's do it. Level I is what he calls the null fit, or the closure neutral limit.
This is where we assume the coupling parameter epsilon is exactly 0.
Right. You start with a simple, incredibly well-understood metal, a control sample like highly purified copper or gold. You perform the thermodynamic and spectral measurements.
Just to set the baseline.
Exactly. You fit your experimental data using standard baseline textbook models. The goal here is to establish the residual structure and prove that when the UFT coherence factor is flat or trivial, when the metal doesn't have any strange structural shadows, you perfectly recover standard Fermi-Dirac thermodynamics.
Okay, so level I is a sanity check. You prove your equipment works, you prove the old textbook still flawlessly applies to simple materials, and you calibrate your baseline. What is level 2?
Level 2 is the two-parameter fit. Now you take a more complex material, perhaps a heavy fermion compound or a strange metal, where you suspect there are structural anomalies at play.
Something messy.
Right. You measure its heat capacity, and you measure its spectral Fermi-edge using RPs. You take those two distinct data sets, and you extract the values for A and B strictly using the thermodynamic and spectral data combined.
You find the combination to the first two safes, and you lock in your parameters.
Yes, you lock them in, and this is the point of no return. Because level 3 is predictive validation.
The ultimate test.
The ultimate test. You take those exact locked-in parameters from level 2, and you use them to predict the non-equilibrium relaxation time, tau-c. You calculate the expected dynamical bottleneck before you even turn on the ultrafast laser.
No arbitrary retuning allowed.
Absolutely no arbitrary retuning. You cannot massage the numbers, you cannot tweak the slope because the data looks a little off. You measure the actual relaxation time with the laser. If the measured time matches the stringent prediction dictated by your locked-in A and B parameters, you have achieved what Lillian formally calls support.
So let's define the outcomes clearly. What exactly counts as support, ambiguity, or falsification in this matrix?
Support is the gold standard we just described. Shared parameter reuse succeeds flawlessly across all three channels, thermodynamic, spectral, and dynamical, and the null controls from level I return standard textbook values. It proves the UFT geometry is real.
Okay, what about ambiguity? Because there's always a gray area.
Ambiguity is the messy middle ground where most physics actually happens, honestly. Ambiguity occurs if a non-zero fit improves only one channel.
Oh, right.
Like we discussed, if it only improves the heat capacity fit, it's hopelessly degenerate with effective mass. Or ambiguity happens if the channels demand incompatible A and B values.
So the lock jams.
Exactly. If your heat capacity data demands that A equals 2, but your spectral edge data says the safe only opens if A equals 5, the theory remains ambiguous. The underlying structure isn't unified. The UFT shadow isn't cohesive.
And what absolutely kills the theory? What defines falsification?
Falsification is stark and unforgiving. It happens if no common profile improves the joint fit over standard Landau models. Or, and this is the most fatal outcome, if the inferred parameters from the first two channels predict the completely wrong sign for the dynamical shifts.
So let's say A and B from the heat and the spectral data mathematically predict a massive relaxation bottleneck. The math says the material should take a very long time to cool down because the electrons are struggling to find their structural coherence.
Oh, right.
But then you fire the laser in the lab, and the material actually relaxes incredibly fast. It accelerates its cooling. If that happens, well, the theory is dead.
Dead on arrival. If the theory predicts a severe bottleneck when the physical relaxation is actually accelerated, the structural hypothesis completely collapses. The UFT cannot exist as formulated.
I am just struck by the sociology of this paper. The author spends 60 pages building this incredibly dense mathematical architecture. He introduces a universal tensor field. But then he explicitly outlines how standard effective mass models might still explain the triad more economically.
It's very rare to see.
He literally hands his critics the exact tools and the exact experimental roadmap needed to destroy his model. It's almost startlingly humble for a major paradigm-shifting physics paper.
And that humility, that strict adherence to empirical vulnerability, is exactly what makes the paper referee safe and scientifically rigorous. Lillian is proposing a structural refinement, not a wholesale, arrogant replacement of 70 years of condensed matter physics.
He's not throwing out the baby with the bathwater.
Exactly. He is offering a new lens. He is saying, if this new lens focuses the light sharply across all three of these incredibly distinct channels, then the UFT is real. If the lens blurs the image or if it contradicts itself, you throw the lens away and go back to Landau. It is the very essence of the scientific method, laid bare in mathematical physics.
Okay, let's take a step back and look at the whole picture. We have covered a massive amount of ground today. We started with a very simple macroscopic idea, a cup of water.
Right.
We visualized standard thermal broadening as nothing more than sloshing the water right at the surface, giving energetic jumps to the electrons trapped at the Fermi level.
The standard, highly successful baseline that relies entirely on energetic cost.
But then we looked deeper, and we discovered a hidden structural grid submerged beneath that water, the projected coherence stemming from the universal field tensor. We learned that electrons aren't just greedy for kinetic energy. They are biased by the closure stability of the available states.
They care deeply about the structural integrity of their quantum apartments.
Right. And that profound structural bias led us to the minimal empirical triad.
Yes, the three safes.
We realized that measuring a simple shift in heat capacity wasn't enough, because physics already has a rug sweeper called effective mass that can mimic that shift perfectly. We had to use the triad as a rigorous, unforgiving lie detector test.
A cross-observable hypothesis.
Exactly. We had to take the exact same structural parameters, A and B, and prove they could simultaneously cause an asymmetric skew in the spectral edge under a spectrometer and a measurable bottleneck in the non-equilibrium relaxation time under an ultra-fast laser.
It leaves absolutely nowhere for the theorist to hide.
It really is an astonishing piece of scientific literature. And as we wrap up this deep dive, it leaves me with one final, very provocative thought.
Oh, I'm intrigued. What is it?
Well, Lillian's entire paper is hyper-focused on the microscopic low-energy electronic sector.
Right.
He's talking exclusively about electrons, Fermi surfaces, and angstrom-level quantum states.
Yes.
But if the universal field tensor, the U, is truly universal, as the name implies, and if this concept of closure stability dictates how energy redistributes in a constrained system, could this exact same mathematical framework apply to macro systems?
Wow, now that is a truly fascinating leap. If the UFT is a fundamental property of space, its shadow shouldn't just fall on electrons.
Exactly. Think about it. Could the way heat flows across an entire continent be structurally biased by geographic or geological coherence, rather than just raw thermodynamic gradients? Or think about a complex macro network like a city's traffic grid, or even global financial markets.
The math could absolutely scale.
Right. When a financial market suffers a shock, a sudden injection of kinetic energy, so to speak,
Yeah.
how does it relax? Could those macro relaxations also be governed by projected coherence redistribution? Think about that the next time you see a massive complex system stubbornly refusing to relax back to normal, acting like it's caught in an endless bottleneck.
It's a powerful thought.
Maybe the system isn't just trying to dissipate energy. Maybe it is desperately searching for its stable, coherent structure.
The mathematics of the UFT heavily imply that structural stability, far more than simple energetic dissipation, is a universal organizing principle. It provides an incredibly powerful, entirely new lens through which to view any complex system striving for equilibrium.
It really does. It changes how you look at the world. So the next time you picture a metal getting hot on a stove, don't just see a chaotic mosh pit.
Right.
Don't just see a messy, kinetic free-for-all of bouncing atoms. Try to see the hidden, rigid architecture underneath it all. Picture the invisible grid of stability, subtly guiding every single quantum jump. Because sometimes, the most profound and universal laws of physics are hiding right there in the structural muddy waters.